Today we're going to try and fill in a gap, and a gap that I think you've had for quite a long time, because you probably know about the pH scale and you've known it for a long time. What we're going to do today is learn about calculations. So how do we get those pH numbers? What do they mean? And if I have it, what can I do with it? And we'll just get that started today, but we'll get the most important step done today. So we're going to need a calculator. Now I'm going to be working with the graphing calculator because I think most of you have this model. If you don't, you'll still need a scientific calculator. It's possible you have one on a computer, pop up the one that kind of came with it, or most modern phones will have the button that we need to do. Now I will warn you that I normally don't like the magic button kind of thing. I like to have things with units. I like to have things that make sense. This one, we're going to be stuck with a button that just push the button because that's going to give us the right answer. Unfortunately, that's going to cause maybe a problem a little bit later, but we'll deal with it when we deal with it. So, a few things that we need to know in order to start bringing some of these bits and pieces together. pH is going to tell us something about how acidic a solution is, and really important thing to remember there is that the more acidic the more acidic a solution is, the lower the pH. So there's a real backwards relationship going on here, and we're going to kind of find out where that comes from without spending a lot of time on it. And so we have this pH scale, and as you go down in pH numbers, it gets more acidic. As you go up in pH numbers, it becomes less acidic to the point where it becomes neutral, and then it becomes basic. And then the backwards thing kind of falls apart because larger pH numbers mean more basic, but that's a story for another day. Second thing that we already know about acids is that acids will produce in solution some hydronium ion. Now you might see it just as a hydrogen ion, an H+. I typically draw the H3O+. And bases, they're going to dissociate or some way or another produce hydroxide ion. And then the fourth thing that is going to be true for acids and bases, that it's strong acids, strong bases versus weak ones. Now today we're mostly focusing on strong acids, and really in this course all we're going to focus on is strong, whether it's strong acids or strong bases. The weak acids and weak bases are going to have to be treated at least a little bit differently, because they don't dissociate 100%, which means I need to do something else to figure out how much they dissociate. The fifth, I guess, I kind of lost count, even though I have the numbers right there, but the final point, and this is going to be really important for us, and also when you do eventually start talking about the weak ones, is that for a strong acid, or a strong base really, but for a strong acid, the concentration that it says on the bottle for the acid is actually the concentration of hydronium. So in other words, if you have, I should have gone back there, but 1 mole per liter acid means 1 mole per liter hydronium. Okay, here's the calculation side of it. There. Now what in the world does that mean? Well, in closer to English, it means that pH is the negative logarithm of the concentration of hydronium ion. Well, what's a logarithm? Well, for us right now, it's going to be a magic button. So you take your calculator and you find the log button. If you have the TI-84, and I don't get any product placement income from this, but if you have a TI-84 calculator, the log button is there. If it's a different kind of calculator, it'll be somewhere else. But if it's a scientific calculator, you will have a logarithm button. So you find it. You make sure you know where it is, because we're going to need two things from it. Number one is we're going to need the button. Number two is we're going to need the second function of it. And you'll notice above that button, probably above it, it's going to say 10 to the exponent x. There's a way around it if you don't have that, but most calculators will have it. So just to find out what it does, you don't have to write this down. It's not directly connected to what we're doing in chemistry, but just so you get a bit of a handle on what's happening with that button, try these. And pause it if you need to, but we'll come back in a second. Okay, so your numbers for your logarithms are there, and they seem kind of weird. And if you were to try some other ones, so some decimal ones, and these ones still aren't directly related to chemistry, but for us, these are going to be a little bit more realistic, because if I think about concentrations, concentrations are usually going to be small, smaller than 1 anyway. Not very often we get a concentration of 1,000. Okay? Pause it if you need to. Try them out. and then we get these numbers. Okay, so I've got numbers like -1, -2, -4, -1.456. What does those mean? You don't have to know this, you don't have to write this down. Maybe you've done it in math already and I'm just spinning my wheels here, but the log button tells you the exponent on 10 that would give you the question. So in other words, the log of 1 is a 0 because 10 to the exponent 0 equals 1. Jumping down 1, the logarithm of decimal 0.1, which is 1 over 100, is -2 because 10 to the exponent -2 is decimal 0.1. Okay. And all the other numbers, you can figure out some exponent on 10 that would give you that number. Why would you want that? Well, it makes it kind of convenient, really, when we're talking about small concentrations. So pH then is the negative log of the hydronium ion concentration. Why negative? Well, if you think back to the decimal numbers that we had for decimal 0.1, the log of that was -2. It puts us, that would get rid of the sign, really. So the negative log of the hydronium ion concentration. So if I had a concentration of decimal 0.1, which is a pretty reasonable concentration, I would have a negative log of decimal 0.1, which I know the log of decimal 0.1 would be -2, so the negative log would be +2. And that then is my pH. So it gives us a semi-convenient way to work with concentrations, especially very small concentrations. Okay, please pause the video, write these down, figure them out, and then we'll come back in a second with an answers for comparison. Okay, hopefully you did that. Those are the pHs that I've got. Those should be the pHs that you got as well. And one thing about pH that's kind of important is pH does not have units. Very, very rarely are you able to put down a number that doesn't have units. Even more rarely are you able to put down a number that you've calculated that doesn't have units. We won't get into why it doesn't have units. Okay, what if we know the pH? Because we can dip a pH meter, we can dip pH paper, we can be told this is the pH. What does it mean? Well, now I know it means something about concentration, but how do I get there? This is the second function button. If you go to the log button and look above it, usually it's above it, in the fine print on the case it'll say 10 to the exponent x. That's the button I want, because now the opposite of the logarithm is 10 to the exponent. So the hydronium ion concentration is 10 to the exponent negative pH. Remember I had the negative log, now I have to do the negative back. So if I had a pH of 1.5, pretty reasonable sounding pH, then the hydronium ion concentration in that solution is 10 to the exponent negative 1.5, which would give you that. Please confirm that with your calculator. That's what you get. If I had a pH of 2.1, okay, please try this out. You'd be one step ahead of me. 10 to the exponent negative 2.1, and I got negative, sorry, not negative, because you can't have negative concentration, but decimal 0.0794. We won't talk too much about rounding right now, but I will say that concentrations do have units. Very important. And finally, if it's a 3.8, then the concentration is that. Now your calculator might have said decimal 0.00158 or something like that, moles per liter. Actually, it wouldn't tell you moles per liter. You need to write down moles per liter, but it might not have put it into scientific notation. It might have 3 leading zeros. Okay, sounds pretty simple and straightforward, and it really is. There's a couple spots where we're going to get confused, like when do I use the log, when do I use the 10 to the exponent x, but it's really important to understand what's going on with pH. Second thing is once we get into bases, things will be similar but a little bit different, but that's coming up soon. Talk to you later.